All right, so what we're going to do now is try to find a way to quantify a galvanic cell, but also at the same time, how do we relate the voltage that's generated from this galvanic cell? How do we relate that back to Gibbs free energy? Okay, so what I'm going to do is go back to this waterfall analogy because that's going to help us lead us into what we're going to talk about here. So give the important factors to describe a waterfall with a water wheel that captures energy. Well, the biggest thing is the height, because the farther that the farther that the water has to fall, that's going to make a bigger difference with how much energy it's going to give you. Okay. Also, the amount of water that's falling will also matter as well. The energy imparted by the falling is the third aspect, but this is a function of the height and the amount of water. Okay. Now, for an electrochemical cell, the factor that describes the driving force that moves the electrons is called electromotive force, or EMF, electromotive force. Okay. The charge of the electron is going to be given in coulombs. The amount of charge flowing through the circuit is called the current. And the unit for this flow is called the ampere. Or, to shorten it, amp. Now, we can define the ampere, in terms of energy. So 1 joule of energy is going to be produced by 1 coulomb times 1 volt. Now, 1 joule per second is called a watt. And 1 coulomb is the charge for 1 amp of current for 1 second. Now, since we have related this to energy, we can specialize the chemically important free energy for a process. Okay, so what we're going to do to relate what we're talking about here to delta G, there's an equation for a cell. We can measure delta G is equal to negative N times F times E. Now, delta G, we know that. That's free energy. Okay. N is going to be the number of moles of electrons in the equation. F is going to be called Faraday's constant. We'll get into that in a minute. And then E is going to be the voltage, measured in volts. This is electromotive force. Or EMF. All right, now why the negative sign in this equation? And so the negative sign, why we want that negative sign is that when delta G is less than 0, so it's got to be negative, that means it's favorable. So that means when the electromotive force is greater than 0, that's also going to be a favorable process. Now, regarding the F term, that's Faraday's constant. What is its significance? This relates coulombs to the moles of electrons. And its value is going to be 96,500 coulombs over 1 mole of electrons. And just like we considered a standard state free energy previously, If everything is at standard state, we could write that delta G at standard state is going to be equal to negative N times F times the electromotive force at standard state. Now, this standard state, however, is going to be a really big thing because that's what we're going to use in order to help us determine standard cell potentials, which is the next part. All right, so we can combine the electrical impact of both half cells in this way, that when we have an electromotive force, when we have the electromotive current cell, and it's at standard state, this is equal to the half reaction, the oxidation half reaction at standard state, plus the voltage of the reduction half cell at standard state. Now, how do we get each of these terms? A direct measurement's not going to be possible because in order for something to be oxidized, something's got to be reduced too. Okay, and you can't do one without the other. Now, just like enthalpy, Gibbs free energy, we have to define a baseline like altitude versus sea level. However, it's quite different than these cases. The baseline for what we're going to be looking at for electromotive force is that we want a reaction to generate no voltage. So we want the electromotive force of this cell to be 0. That's our baseline, 0 volts. Okay, and the way that we're going to get there is that we can have two half reactions going on. One half reaction says this: 2 moles of H+, which is going to be aqueous, and you have 1 molar concentration, plus 2 electrons yields hydrogen gas. Again, this is going to be gas, 1 atmosphere. All right. If I was to write the backwards reaction, H2, which is a gas at 1 atmosphere, is going to break apart to give it 2 moles of hydrogen ion, 1 molar concentration. Okay. Both of these half reactions will generate 0 volts. Now, we call this, when we see this, this is called the standard hydrogen electrode. Or SHE. And this is our baseline because these half reactions generate no voltage. All right, so a short version, we can, using this baseline, we can generate a table that we can match all these voltages up. This table is called the standard reduction potentials. Okay, and a table will appear like this. Okay. All right, so what's kind of nice is that you've got the half reaction. It's going to be listed as a reduction half reaction. You're going to get the voltage for that cell. Okay, as you're going from the bottom to the top, you're increasing it becomes a stronger oxidizing agent. As you're going from the top down, you're increasing the stronger reducing agent. All right, so several things to note about this table. Half reactions are all written as reduction half reactions. Okay, so that's the first thing. Second thing, the half cell potentials are written as standard reduction potentials. And they're written in order of decreasing standard reduction potentials. Okay. Now, how does this table compare to the activity series in Chapter 4 back in Gen Chem 1, other than the addition of electromotive force? There's two major differences which can lead to conclusions, so give the differences. So remember that the activity series were written as oxidation reactions. As oxidation half reactions. Okay, so that's one difference. The other is this. Strongly reducing agents are going to be at the top of the activity series. And in the cell potential chart, they're at the bottom. Okay. So, that being said, we can use this table to answer the following questions. Which is a stronger oxidizing agent? Nickel 2+ or hydrogen peroxide? So what we're going to do is go to the table and find those two. All right, so looking at the table, we want to find hydrogen peroxide, and let me highlight it. It's right here. All right, and then nickel 2+ is right there as well. Okay, so which one is going to be the stronger oxidizing agent? Well, because hydrogen peroxide is actually near the top, because it's higher on the list than nickel 2+, that one is going to be the stronger oxidizing agent. All right, so to answer that question, which one? It's going to be H2O2, hydrogen peroxide. It's higher on the table. Okay, which one is a stronger reducing agent, silver or water? So going back to the table, we're looking for silver and we're looking for water. All right, so let me get the highlighter out. All right, so silver, Ag. Here's Ag. Okay, and then water, here it is. We've got two different equations to look at. All right. So for this one, so which one's going to be stronger? Is it silver or iron, or silver or water? And we're looking at the stronger reducing agent, which, remember, reducing agents are going to be on the bottom. So the ones closest to the bottom are going to be the stronger ones. So in this case, since silver is below either of the water equations we've got, silver is going to be the stronger reducing agent, okay, because it's lower on the list. Okay, so now what we're going to do is start using these cell potentials and start writing equations. Okay, so let's do an example of how this all works. So what we want to do is write the reduction, reaction, and potential for silver. So that was silver plus, which is aqueous, plus 1 electron, yields solid silver. And the potential, the cell potential for that was 0.80 volts. Okay, and so we want to write the reduction, reaction, and potential for iron to iron 2+. Okay, so looking at the periodic, looking at the standard reduction potentials, what we've got is let's see, we've got Fe2 plus, which is aqueous, plus 2 electrons yields solid iron. And the cell potential for that one is going to be negative 0.45 volts. Okay, now for a spontaneous reaction, what combination of these reactions would occur? Give both half reactions and the overall reaction all with electromotive forces. Okay, so we know that we got silver, and silver generates 0.80. Iron is going to generate 0.45. So what we're going to do, we need to flip the iron around. All right, so also keep in mind that you've got 2 moles of electrons in the iron reaction. You've got 1 mole of electrons in the silver. So here's what we're going to do. Let's start with the silver reaction, and I'm just going to write it. Silver plus iron, okay, plus 1 electron yields solid silver. Okay, and that electromotive force, the cell potential is 0.80 volts. Okay. Now what I'm going to do is flip the second reaction. Because remember, the electrons can't be on the same side. So I'm going to write solid iron gives us Fe2 plus and 2 electrons. Now by doing so, if you notice, the cell potential is negative because we flipped the equation. That's going to become a positive 0.45. Now, the number of electrons have to match in both equations, so that means we're going to have to multiply the first equation by 2 in order to get the number of electrons to match. But here's the other thing. Even though normally, when we did this with Hess's law back in Gen Chem 1, if we double an equation, we got to double the enthalpy. Now here, we won't double. So we don't double this value. Okay? So we leave it as 0.80 volts. So when we add up these 2 half reactions, we're going to get this. 2 silver ions plus solid iron gives us iron 2 plus solid silver. And if we add up those 2 values, the cell potential at standard state should be 1.25 volts. Okay. Now, under what conditions would you be able to measure this voltage value? You would be able to measure this under 1 molar concentrations. Because remember, the voltage changes with concentrations. Okay. All right, so that is pretty limiting because you're specifying, instead of, previously we didn't really care what the concentration was. Now we're stating that it's got to be 1 molar concentrations. And that does seem to be really limiting for us. What we recommend, though, there's actually something that's pretty cool that's coming up that allows us to use that. So hang in. The next video we get to see why that's okay for us.